All right, so question number 9 is about a car driving around a circular track, yes? So this is a fairly common sort of setup for a circular motion style problem. All right, something that I did not do when I wrote this homework assignment that I have since edited, actually that's not true, I need to write myself a note so that I will do that, I don't know why I said that. 5.2 edit. There we go, we'll do that. Problems 7, 8, and 9 in particular are problems where if you get stuck, I really think that taking a minute to make a free body diagram for the object that's going in a circle will make your life easier. Okay? Because it helps you make some connections between the different forces. All right? So problem number 9 is about a race car. Well, here, let's write down what we know. So problem number 9, here we go, is about a race car which has a mass of 1,200 kilograms, and it is driving around a circular track which has a radius of 150 meters, and then it tells you that the coefficient of friction between the tires and the track is 0.6, and it wants to know what is the maximum velocity at which the car can go around the curve. Good? All right. So, largely because I don't have a race car to model, I don't have a race car that I can show you. Here's a race car. Let's look at it. I'm going to pause the discussion of this, and let's take a quick look at number 7, which is, instead of being about a car driving around a circular track, it is about a spider. Spider-Man? Anybody? No, you guys don't even care. On a turntable. All right, so, oh, that was really loud. So what these have in common is whether it's a, that was really loud. Oh no. All right, so whether it's a car driving around a circular track or a spider on a turntable, in both scenarios you've got an object on a flat surface going in a circle where there sort of doesn't seem to be anything touching it other than the thing that it's sitting on, right? Okay, so the question then becomes sort of what forces are acting on it and how is it going in a circle? Okay, and in the video I talked about it, but sometimes I worry that, like, you know, you watch the video and you go, oh, cool, well he said that's the force, so that must be the force, but maybe you still don't completely understand it, right? So let's talk about what's going on here. All right, so imagine the spider on the turntable. If the turntable turns, he goes in a circle, right? So there must be a centripetal force on him, right? Okay, so let's take a second and think about this for a minute. So, quick tangent. We're going to talk about number 7 for a minute. Here is the record. Here's our spider. 1, 2, 3, 4. Oops, 4. 5, 6, 7, 8. That's the ugliest spider I've drawn all day. I apologize. Don't take it personally. All right, help me out, you guys. What forces are acting on the spider? Gravity. Okay, cool. So gravity is pulling the spider down. Cool. But as you can see, the spider is not, in fact, falling, and that is because of normal force. Okay, cool. And those two guys are probably equal, right? Or they have to be, in fact, right? Because he's not moving up or down, right? So then the only other force is, I know he's going in a circle, so there must be a centripetal force pushing or pulling him in towards the center of the circle, right? Please hear me say this. This free body diagram is not complete until you tell me where that centripetal force is coming from. Okay? So like in the case of the bee spinning around on a string, where does the centripetal force come from? The string, right? So for this one I could write centripetal force equals tension, right? Okay? Or if I'm looking at a satellite orbiting the Earth, I could write centripetal force equals gravity, the force of gravity, right? Okay? So sometimes it's not that hard to figure out where the force comes from. But here, I don't see anything pushing him, right? So where is that force coming from? would happen if I started spinning the disc faster and faster and faster? He'd eventually fall off. Okay. So, but in order for him to fall off, he has to get from here to the edge, right? So what's going to happen between, I don't want to say that, I don't want to use that word. What's going to happen before he falls off? Say it again. Okay, yeah, there's not going to be enough static friction. I don't like the word overcome because there's nothing pushing against static friction, but you're right, there's not enough static friction, and so he begins to slide, right? Okay, so watch. Do you guys all agree that he is not sliding right now? Oh, and he's going in a circle. Not sliding, going in a circle. Not sliding, going in a circle. Oh. Once he started sliding, he was no longer going in a circle. Right? And so what that's telling us is once he starts sliding, there's not enough static friction to prevent him from sliding, and so he goes outward. So what was pulling him inwards or pushing him inwards? Static friction, right? So this inward force that I'm missing here is my force of static friction. Make sense? All right, now it turns out that, well, is everybody good with this? Okay, now it turns out that the car is the exact same thing, except here with the car, the reason the car is moving is not because it's on a spinning disc. The reason the car is moving is because it's got wheels that sort of keep pushing it forwards. But think about it, what's going to happen? Imagine that you turn a corner in your car too quickly. What do you hear when you turn a corner too quickly? Skidding, right? The tires go, right? And guess what? That sound is the sound of your tires sliding across the road. That's kinetic friction. And the goal is you don't want to slide, so it must be static friction that's preventing you from sliding and making you go in a circle. Does that make sense, you guys? We good? All right, so for number 9, the free body diagram for number 9 is almost identical to this, except instead of having a spider, we have a car. So let's draw the car. I'm going to draw the car from a front view. So it's going to be like, the car is going to be coming out of the board at you like this, and then driving around in a circle like that. Cool? So let's draw that. So here we go. Here is the front of the car, headlights, windshield, driver, steering wheel, hands at 10 and 2, wheels, wheels. So there's our car. Let's see, we need a road for it to be driving on. We'll draw the road using black. Does everybody understand my weird sort of three-dimensionally drawing there? Thank you. All right, so what forces are acting on the car? Gravity. Oh, and in fact, actually, now that we're doing number 9, I know some numbers here. I can do some calculations. I can find my force of gravity. 1,200 times 9.8 is 11,760 newtons worth of force. Good? All right. And somebody mentioned there has to be a normal force so that the car doesn't fall through the road. And that normal force has to equal our force of gravity. Okay? And because the car is traveling in a circle, there must be a centripetal force. And once again, we have to identify where it comes from. So where does it come from? Friction. What kind of friction? Static. Is everybody okay with why it's static? A lot of times people go, well, wait a minute, the car's moving. Shouldn't it be kinetic? You guys understand why? The difference between static and kinetic isn't whether the object is moving or not moving. The difference is whether the object is sliding or not sliding. Okay? Okay, cool. Now, can I figure any of these things out? Well, check it out. If I'm trying to maximize the velocity that the car can go at, does it make some intuitive sense to you that I then want to maximize my static friction? Right? Because that would give you the circumstance where the car can go the fastest when you've got the most force on it, right? Okay, cool. So we can find our force of static friction max. Max, do you go, oh, that's me, every time I say that? That's fun. I'm going to start calling it force of static friction Todd. Because that's my name. Sorry. I am worried you guys don't know how funny I am. Oh, wait, sorry, what am I doing? Sorry, I'm being distracted by my own dumb jokes. Static friction times normal force, right? So, our coefficient of static friction is 0.6. I said 0.6, 0.6, 0.6. Oh. Times the normal force. And that gives you, I think it's 7,056. Oh, cool. So that's what goes over here. Good? Any problems? All right, so great. So I figured out a whole bunch of garbage about the forces on the car. But the question doesn't ask about the forces, it asks about the velocity. So what's the connection? How do I get from this drawing to something about the forces on the car? Well, some of you guys have your equation sheet out. Take your equation sheet out and look at the circular motion section and see if you can find an equation in that circular motion section that connects forces to velocity in some fashion. It's the equation that ties those two ideas together, force and velocity. Anybody see an equation that has both force and velocity? You're nodding, Brian. What do you got?
Force equals mass times acceleration, which also equals mass times velocity squared over radius.
Yeah, good. Yeah, we learned that your centripetal force can be calculated by doing mass times your centripetal acceleration. But remember, centripetal acceleration is just v squared over r. Good? And I am happy because I know that my centripetal force is the same as my static friction. So that's got to equal the mass of the car times the velocity squared divided by the radius, and then solve for v. That gives you whatever the answer is, 22 or something like that. Is that at all right? I'm doing that totally from memory. 29, okay. Does that make sense, you guys, what's going on here? Because once you get the free body diagram down, it helps you make connections between things, right? You know your up and down forces have to cancel each other out, right? So you know here are sort of, for these types of problems, here are the things you know. You know that your net force vertically is 0, so your ups and downs cancel. You know that your centripetal force, in this case, is provided by static friction. We know centripetal force is mv squared over r. We know static friction is coefficient times normal force. And so just by manipulating these three ideas, most of the problems are going to be set up where either you know the coefficient and you have to find the velocity, or number 7 was the opposite. You knew the velocity and you had to find the coefficient. But the drawing still looks the same. All right, thermometer, where are we at, you guys? Good, Aiden, you good? Yeah? Okay, so let's talk then before you start the karate check. Good? All right, everybody good? All right, so that was the one that people asked about. Is there a part B that I keep forgetting to do in my other classes? It probably is, or did I do it already? Oh, find the acceleration, yeah. So just v squared over r, right? Okay, so I know not a ton of people asked about it, but I would still like to request permission to at least talk about number 8. I don't need to go through the whole thing. But there's an important distinction between number 8 and this. Okay? So for these problems, the car on the racetrack and the spider on the turntable, notice both of those scenarios have the object on a horizontal surface, right? Okay? And remember that in those cases, you've got a normal force. please remember, your normal force does not always have to point straight up. It often does, but not always. All right, for example, if I take this box and put it on, so there's my normal force pointing up, right? But if I put it on an inclined plane, whoa, failed. Remember, the normal force is perpendicular to the surface, right? Okay? And as the inclined plane gets steeper, the normal force gets closer and closer to being horizontal, right? Good? So I know we talked about this. I remember teaching this when I was still, you guys don't care where I was, but, so imagine this for a minute. Quick tangent number 2. What did I just do with that box? All right, so here we go. This is a box. You can tell because it's a box. I'm going to hold it right here. So right now I am pushing that way. And I am conscious of the fact that even though I'm pushing it that way, it's not moving that way. And I'm also conscious of the fact that it's somehow not falling, even though I'm not physically like holding it up, right? If my force isn't upward, my force is sidewaysy, right? So there's got to be something holding it up, right? So what's the something? Well, to figure that out, let's make a quick free body diagram for this. So whatever box held against a wall. Here's our drawing, here's the wall, here's the box. I was pushing it this way. How come it didn't move that way? How come it didn't move through the wall? It's a solid object. What else? What do we call that force, you guys? Force of wall. There we go. Normal force. Isn't that a normal force? Right? In the same way that gravity prevents our spider from going through the record, here, did I say that right? I didn't say that right. In the same way that the normal force prevents gravity from pulling the spider through the record, here, the normal force from the wall prevents me from pushing the box through the wall. What has to be true about those two forces? They have to cancel each other out, right? They have to be equal, right? No matter what. Okay, and then gravity's pulling this thing down, but something is preventing it from going down the wall. Can you? All right, I'm getting tired. I'm gonna loosen up a little bit. Oh, now it's sliding. So before it wasn't sliding. Now it's sliding. What's preventing it from sliding? What kind of friction? Static, right? There has to be static friction here, right? And to prevent it from sliding, we need the maximum static friction to be at least as big as our gravity. Follow? So, cool. What do we know? I know that the force of static friction maximum is equal to my coefficient of friction, which I don't have any control over, that's just a measure of how rough the two surfaces are, times the normal force. So I want this force of friction to be big. So what do I do to embiggen this maximum static friction force? How do I make the static friction force bigger? Good, make the normal force bigger. But how do I do that? How do I make the normal force bigger? Push harder, right? Because if I push harder, then the normal force has to get bigger. And if the normal force gets bigger, then my maximum static friction gets bigger and will hopefully be enough to cancel out gravity. Follow? All right, now, problem number 8 is about the rotor. That's the amusement park ride where you're in the giant round room, standing against the wall, the room starts spinning and you stick to the wall, right? And then they drop the floor out and it's cool and you stick to the wall and you don't slide down the wall, just like this box doesn't slide down the wall. Okay? The only difference is this. In this problem, the reason that there's a normal force is because I'm pushing And the normal force needs to be there to prevent the thing from going through the wall, right? With the rotor, with the amusement park ride, top view, here's the room, it's spinning tin can. Here's Sally, who's inside the room. She's got pigtails, so we'll draw those there. Little part down her hair. So she's spinning around in a circle. If there was no force on her, she would go through the wall, right? Because she'd go in a straight line. But she doesn't go through the wall because there is a normal force moving her in a circle. You guys see what I'm saying? It's the normal force pushing her inwards that provides the centripetal force to make her go in a circle. Good? All right. So this is kind of the idea, but this drawing doesn't really help me any because I can't see where gravity is on this, right? Because gravity would be down into the board, right? So let's make a new drawing. So here's the top of the ride. Here's the walls. Here's the floor. Here's the other floor that you can't see because you can't see through stuff. All right, let's go ahead and draw a pen. How about black? There we go. So here's Sally. Pigtails. How happy she is. She's excited. She's on the rotor. All right. Now, what forces act on Sally? Gravity. Very good. Gravity is going to pull her down. The normal force we just decided is pushing her inwards, right? And it has to be there to provide the centripetal force, right? But still, she doesn't slide down the wall. Why not? Because of static friction, right? Follow? So once again, in this problem, your up and down forces have to cancel, and your inward force provides your centripetal force. So you've still sort of got the same equations that we had in that last problem. You're still going to know that, oh, well, my static friction is coefficient times normal force, and I still know that my centripetal force is mv squared over r, and I still know that my net force vertically has to be 0. And so once again, I can say, how much does the coefficient of friction have to be to prevent her from sliding? Or I can say, so that would be, you know the coefficient, find the velocity. I could say, if you're spinning at this velocity, what does the coefficient of friction have to be? Make sense? All right, so really quickly, I'm almost done talking at you. That one there, and then haha! Success! All right, so look at these two drawings. So we've got the car on the circular track, or the splitter on the record on the right, and we've got the rotor, or the salad spinner, or chocolate chip in a blender on the left, right? Both of them have the same, well, 3 forces, right? They all have gravity, normal force, and friction. But notice the roles of those are switched, right? On this one, it's the static friction holding her up. On this one, it's the normal force holding it up. On this one, it's the normal force providing the centripetal force, and on this one, it's the static friction providing the centripetal force. Does that make sense, you guys?
Is that because the car is moving? Like physically?
No, because that would still be true for the spider. Is that what you're asking, or
No, yeah.
are you sure I'm worried I didn't answer your question?
No,
Okay.
I get it.
Okay. So these drawings are important because they will help you solve the problems. Okay. So if you get stuck on one of these circular motion problems, make the free body diagram. And please don't just label a force centripetal force unless you also tell me where it's coming from. Okay. Questions? All right. Those are the things I wanted to talk about. Do you guys have other questions that I did not get to? Alrighty then, here's what is going to happen when I, here's what's going to happen right now. I'm going to pass out the target checks. You're gonna look at the target check and you're gonna go, cool, I understand this now, because I worked on homework and I watched the video, and Mr. Hacker just went through some stuff, and I'm gonna do the target check. Or you're gonna go, I have no idea what's going on, please help, and we'll go to one of the lab tables in the back and we'll work on stuff. And then you can do the target check over the weekend. Which brings me to due dates and stuff. I, for whatever reason, I'm having a really tough time figuring out the pacing with this hybrid thing. I wrote one schedule that was way too fast, and I ended up landing on this other one that I think is way too slow. I don't know why I didn't just find the average, but I did. So here's what we've got. You've got the target check right now. If you finish it, awesome, put it in the third hour bin here. All right, if you do not finish it, take it home over the weekend and bring it in to me on Tuesday. Okay? Tuesday in class, we're going to do two things. I will do a target check Q&A for anybody who struggled with target check. And I will do a centripetal force lab Q&A for anybody who still has questions before they turn it in. All right? That lab is due next Friday, so 1 week from today. Okay? The only other thing you got to get done next week is watch video 5.3 by Wednesday, by that virtual class. Okay? Cool? Questions? Issues? Concerns? Anything? Yes?
Do you have an extra calculator?
I do. So there's a whole bunch of calculators on the wall over there. Please help yourself. You don't even have to ask. That's what they're there for. Alrighty. Any other questions before I pass out the target check? All right. There is a typo on this, which somehow nobody yesterday caught, but then my 6 hours went, what? Question 1C says, a chocolate chip of lettuce spins around in a salad spinner thing. It was originally a problem about a chocolate chip in a blender, and then for some reason I changed it to a piece of lettuce in a salad spinner, and I somehow didn't delete the chocolate chip part. So it's actually about lettuce, okay? One for you. Oops, one for you. We'll stop and one for you now. Annoying. Dang, all the time. What is your turkey? What is that? What's that? Pistons? That's a new envelope? I've never seen that envelope before. Okay. Really? Google this, Ian. Get to the bottom of this. Max. All right. What's wrong?
Oh, they're amazing.
Is it only mine?
No, it's all.
Okay. You give me like a. Where are we at?
Yeah, I don't know. I was
Practice. Back here, or work? All right, 8 and 9 are going to go back and do a little practice. Anybody else want to join us? Anybody else struggling a little bit? Oh yeah, let me sign past the stupid rules. Oops. You are very welcome. Cool. All right, come on back, my friend. Grab some scrap paper, some different colors of pens, so I can explain stuff in color. Black. There's a black pen here somewhere. I thought. Oh, here it is. Identify where the centrifugal force comes from. It's always going to be A either pushes or pulls the object that's moving in a circle, a circular object. So really, all you got to do is figure out what's doing the pushing or pulling, and then decide if it's push or pull. So maybe over the weekend, go back and watch that again. But yeah, it was kind of like that. Big ball in the chain and spin it around, clip in there, try to go as hard as I can. So, while they're there, the ball will spinning around in a circle. What provides force? Sure. So the guy who's spinning around, pulling the hammer, right? If he lets go of it, then it will fly upwards. Good. All right. How about like but not around. How about this? I'm shrinking or my pants are stretching, but they are not staying up like they should. Oh. Sorry. Good. Right. That's pretty good. And I think the other one is this. Yeah. Good. There. Good. Alright, so that is one of the skills we have to see. And I think those are the only four ones I can possibly do. Good. Alright, so then the rest of it is just the power. So like, suppose that I know where to do that. It's gotta be just the, yeah, so this is 0.1. The radius of this practice circulate through is 45 meters. And discover the spin at a frequency of If you need something, holler at me, you guys. equation is incorrect. Where is the centrifugal force come from?
Yeah, it's a double force.
So the equation that are here, and that's why you know the equation for static friction. Normal. Normal force. Force is always upside down. Square for R. So we don't know if we're looking for the coefficients, that we need the velocity. This equation here is not velocity. Somewhere. Need one. Okay. One back there. No outward force. Remember, you guys, when you've got an object moving in a circle, there's never an outward force. You have an inward force making it go in a circle. When you take away that inward force, that's when it flies out. Not because something's pushing it out, but because nothing is pulling it in. Very, very important, Eddie. Very important. Rock and rolling for a minute. Oh, whoever's computer is charging over here, the computer's plugged in, but the table isn't plugged in. So I'm going to move it to somewhere where it will charge. You are welcome. Hear my name. Oh, you're welcome. Absolutely. Just plug it in. I'm a long side for target check. I'm sorry, guys. Yeah, absolutely. Pass it over by under the pot. Okay. Fill everything out and I'll sign it for you. Awesome. Oh, I'm sorry.
No, no worries. Can I take over this one? Okay, so I did this.
Yeah, this all looks great.
I'm trying to think about how I can put frequency.
Good question. You have your equation sheet handy?
Yeah, I have it right here.
Right. Are there any equations that have frequency in?
This one,
Yeah, this one's sort of circular though, right? Like you need the frequency to find a period, you need the period to find the frequency, so I don't know that buys us a ton.
like these ones.
Oh, yeah. Oh, I know the velocity, I can find the frequency.
I don't know if I see it.
Okay, so how can we use, so we've got some information here about forces. Is there any way we can use that to find the velocity?
Oh, like this one? Okay, yeah.
Does that make sense?
Yeah, that makes sense.
So this one's, it's very similar to the one we did on the board with the one extra step that once you get the velocity,
Yeah.
you gotta go one step further to find the frequency.
Yeah, interesting.
You were very welcome. Good work. Oh, am I still recording? Probably am. Ooh, am I still recording? Boop, boop. I am. It's exciting. Where's my mouse?